All right, so let's talk about the mechanical properties of these polymers. So a lot of the information for this section, a lot of it you can just find in your Callister reference from MSE 201, 301. And then there's also ASTMs that we use for the actual testing of the polymers, and you can find some of that information in that ASTM. And so that's kind of what I'll use for this module. So the first thing is just to kind of talk about the general types of stress-strain behaviors that polymers exhibit, because there's a pretty wide range. And so the first one is you might just see something like A here. So this looks pretty familiar to some of the other stress-strain behaviors that we see, for example, ceramics or glasses or some brittle metals. And so this is just an example of a brittle polymer. So basically it just has an elastic behavior, linear elastic for the most part, and then it breaks. So there's no there's no noticeable plastic deformation. So there's a lot of amorphous polymers, and those can have very brittle behaviors. And those networked polymers, for example, can have this type of behavior. So when you see a brittle material, that can start to tell you about the structure of the polymer. Next, you might see something that looks like this. So we see the more elastic region, and then we see this sort of yield, and then it dips down and it comes back up and it breaks. So this is B. And so in this case, we notice that there's quite a bit of strain. So this is fairly plastic. So this is a kind of plastic material. So a lot of times we colloquially call polymers plastics, but that's kind of a misnomer because not all polymers have this kind of plastic or ductile behavior. And so these tend to be things like semicrystalline polymers where there can be a lot of stretching of the chains and so forth. And so that's what we have here with this kind of plastic behavior. And the third kind of general category we might see is something like this. So this is where we have, so this is C. So this is where we have sort of a very long extension, but this is actually all elastic. So this is just nonlinear elastic behavior. And so these are things like elastomers. So things like rubber bands, right? So you can stretch them a long ways, but it's purely elastic. If you release this, it'll go back to its original shape. And so you have to take them a very long way before they break here. And so, but a lot of times they'll exhibit sort of non-linear elasticity. So they're going to look different than the brittle materials, even though these are both purely elastic behavior. Okay, so that's just something to consider, is the basic shape of your curve will tell you quite a bit about the type of material that you have. All right, so now let's look at some of the various properties that we want to be able to extract from these stress-strain curves. So let me just redraw the stress-strain. And let's say we have a curve that looks like this. So this is where it breaks. So tensile strength is defined a little bit differently than it is in polymers. Here, this is typically referred to as tensile strength at the fracture or break. So the tensile strength in metals doesn't always happen at break. And so here we're defining it a little bit differently. So in fact, this is the tensile strength, or TS. So that's one kind of difference in polymers, is that here we're referring to tensile strength at break. And so this is quite easy to calculate, right? We just take the value where it breaks and then calculate the stress at that point, and we've got our stress value. So essentially, the equation for this is sigma TS for tensile strength is the force at fracture divided by the original area, because we're using the engineering convention in this case. Same thing if we want to look at elongation. We're typically talking about the elongation at break or fracture. So just the convention we had there. And so this is going to be the strain that we have. So essentially this percent elongation is going to be equal to the change in length over the initial length at fracture. So if you remember, this term is equal to the strain at fracture. So basically it's that value times 100, which will give you the percent elongation. So that's another easy one to calculate. So this is, in fact, strain at fracture times 100. So these are both pretty easy to calculate from the curve. So let's look at another one that we want to look at, and that is yield strength. So yield strength, again, this is one that we calculate a little bit differently than in metals. So let me give you a different curve for this one, just to illustrate some of the differences. So stress strain again, but let's say I have a curve that looks like this. All right, so again, the way we define tensile stress is that it's the value at fracture, right? And the yield point, so this term, in metals, we use the offset method for most cases, you know, where we had to make the offset of the elastic portion and find that value. Well, it's actually easier in polymers. It's, instead of defining it by the offset, what we do is we simply take the force at yielding, if there is yielding that occurs, and divide it by the area. So effectively, we just take that point where essentially it's, you know, the max before it drops. So this is our yield strength. And so we just take it as the force at yield divided by the original area. So instead of having to do the offset method, we just take the point at which it yields. So that's makes it a little easier for us in this case. So we don't have to do the offset. So 0.2% offset method, not needed. Don't even worry about it. All right. So the last thing that we want to talk about is the modulus. So Young's modulus, you know, when we're talking about metals, that's the slope of the linear elastic region. So here, a lot of times we just refer to it as the modulus. We don't call it Young's modulus in a lot of cases, so just the modulus. And this is really done in the same fashion as metals and so forth. So again, let's kind of zoom in on the elastic portion. So let's say we have a linear elastic portion. So we have something like that looks like this. In a lot of cases, we'll have what's known as this little toe region down here, and then we'll have yielding. But you'll notice in between, right, in this region, we have a linear elastic portion, right? And so we can basically take that slope, and that's our modulus. So just a very similar way. But oftentimes we'll have this little toe down here, and a lot of times it won't look super nice and linear like it does in metals. So it can be a little trickier to find the modulus because it's not as linear as it is in the case of metals. But again, it's just the slope, so we're talking stress over strain, a linear fit of that region. So there is another way to measure it, So if there's difficulty, if there's no linear elastic region, then what we can also do is find the secant modulus. And so in this case, let me draw a different one for you. So in this case, we have something, sorry for the text messages there. So we have something that looks like this. And so we have to basically find the maximum slope. And so that's this portion here. And then we find the intercept with the x-axis, so this point, which I'm going to call B prime, and then, so this point where it intersects the y-axis is called B prime. And then we take some percent strain. So we basically kind of pick an arbitrary point on the plot, but we make sure it's a uniform value here, and we fit the line between that B prime and that curve. So it's got to, so essentially that arbitrary point that you pick here, I call it G prime, that's got to be uniform across all your samples. But then we would effectively find the slope here, and this is the secant modulus. So I don't think most of you or any of you should have to do this, but just kind of keep in mind that if it's not linear elastic, then you have to do the secant modulus method. All right, so those would be some of the quantities that we're looking for when you analyze your tensile testing data. So first thing is you should always look for what type of curve you have. That tells you about the type of polymer. And then you can calculate things like the tensile strength, the yield strength, percent elongation, and the modulus. And these will all be things you can use to characterize your polymer and also identify what that polymer is.